So some of you should take off the mute and tell me, yes, you can see it.
Yep.
Yes.
That's good.
Okay. So what I told you when we started last time was that all this electromagnetics, including X-rays, can be understood in terms of Maxwell's equations, shown here, and that from Maxwell's equations we can get the wave equation, which works for the propagation of all radio waves, infrared, visible, ultraviolet, and X-rays. And what we have to do is we have to write an expression for the current density J. It's like amperes per square area, amperes per area, current per unit area. So I told you that, okay, this is where we're started. Sort of, I didn't use the phrase, but I might have said, they're God-given. We're going to work with them. What I could have, but then I went on to derive a lot of things from that, which are in the book. And I think what I should have done instead was something like this. So it's not a total summary of what we did, but I could have said, okay, from those Maxwell's equations, we can obtain a wave equation. It's described in the book. In fact, in one slide, we do show it, and I think I repeat that today. And when we combine those equations, we find that they form a characteristic wave equation, the same wave equation you see for acoustical waves, sound waves, water waves, atmospheric waves, light waves, and there's some phase velocity in that equation. And when we look at that in the mathematics, this is what it was, where the epsilon zero and mu zero came from Maxwell's equations, and they just appeared in the wave equation, and it is the phase velocity. And the phase velocity is like the crests of the waves. What is the speed with which the crests are moving? We need to say something about phase velocity and group velocity, but this is phase velocity. Simply, what is the speed with which the crests are moving? I could have also said, and saved you a lot of grief probably, is that if we combine Maxwell's equations in the right way, we can get a relationship between the magnetic field and the electric field, which is basically what's shown here. That for a transverse electromagnetic wave, they're orthogonal. The K0, lowercase k, bold, vector, subscript 0 means it's a unit vector. So this is a unit vector in the wave direction. So K in the wave direction crossed with the electric field, which is transverse, gives you a magnetic field in the third direction. So, and we need this relationship, okay? And so to get into some of the properties of X-rays, like both scattering and refractive index and other things, we need this relationship. In fact, what we find that we want to know is what is the power flow, power per unit area, in fact. And that is, in electromagnetics, it's called the Poynting vector, shown here with a bold S, meaning vector, and it's E cross H, okay? Which, since we know a relationship between E and H, we can write in this manner. So this is a vector power per unit area, and by the way, the magnitude of that is what we call the intensity, which we typically write in watts per centimeter squared. Okay, so the intensity in watts per centimeter squared is going to be this quantity without the unit vector. This is giving a directionality. This is the vector part, vector direction of this, okay? So these are relationships we need to know. Having used this one, we don't use it so much anymore, but this relationship between intensity and the magnitude of electric field squared for this transverse wave, that we're going to use over and over and over, okay? Just numerically, the relationship between intensity and electric field is as follows, where the E0, this means that I've written the electric field as something like E0 is a magnitude, cosine omega t. So I'm saying that the wave is propagating along with an electric field, something like E0 sine or cosine omega t. Okay, here it's a scalar. And this number, and this is the intensity averaged over a cycle, okay? Okay, which winds up being over a sine squared or a cosine. So this is the relationship between intensity and electric field. And we'll wind up using it many, many times in the class. For the high harmonic people, it's quite important, okay? And if you reverse this, you have a relationship here that the what is the electric field when there's a certain intensity? And you'll use these relationships in the homework, which goes out on Friday, okay? And by the way, just to remind you, when we use this bracket here, it means that, for instance, here, where there's an intensity, bracket watts per centimeter squared. So if the intensity was 3 times 10 to the 14th watts per centimeter squared, the only thing you'd have under this square root sign is the number 3 times 10 to the 14th. This means just put the intensity in these units. You don't put the units. The units are volts per angstrom here, okay, which sometimes we'll make volts per centimeter because it's a common unit. You'll see them. In fact, I told you, you should look at those at the errata and copy out important things into your book or whatever you're doing, because there are the small but annoying slip-ups there which need to be corrected, okay? And I also told you that there was a list of equations. It's more or less by chapter. And these are in it, but they're probably in it for chapter 7 for the high harmonics because it's so important there. They may also be in it in chapter 3. I don't remember, but you do want to pay attention to those. It'll make life easy for you. Okay, so here now we'll go a little bit faster. What I told you was that in chapter 2, which we're going to complete today, we're dealing with electromagnetic radiation incident on point particles, a single electron, a single free electron, a single bound electron, meaning that it's part of an atom. So it might be the electron in a hydrogen atom, okay? And then we'll look at a bunch of electrons, an atom, a multi-electron atom will be the third thing we'll look at. And then we have a lot of these point particles, but they're somewhat separated and they're moving in time. They're statistically, we have statistical measures of where they are, radial, etc. But anyway, so we're going to look at that and we'll wind up here introducing the so-called atomic scattering factor, okay? And then for chapter 3, which we'll start next class, I believe, we'll be looking at what these same Maxwell's equations and many of the same relationships used to study what happens when the X-rays are incident on some material, thin film, what gets reflected, what gets refracted, okay, how does the scattering we learned here carry over to here? And we'll introduce a propagation of X-rays in the material, which we're going to represent by this. And these delta and beta are going to be closely related to the atomic scattering factors. Okay, I'm not going to go through this because we did it, but here. So here's showing a plane wave coming in with a certain wavelength, and there's some object here, and the radiation comes in and it's scattered. So this is not just for X-rays, this is for any wavelengths, and in fact, doesn't have to be for X-rays, it could be for billiard balls, or electrons being shot at some ions or something and deflected, okay? So the cross-section of this, the area it presents to the incoming radiation to scatter, to redirect radiation in all directions is defined this way. It's the power scattered in all directions. So this P is in all directions. If I wanted the power per unit solid angle at some angle, I would have put here dP d omega, okay? So the cross-section is defined, 3 lines, as the total power scattered, sent in all other directions, divided by the intensity, okay? And there's a question of, is that radiation going in all different directions? Is it isotropic, equal in at all angles, or is it anisotropic? And is there a wavelength or energy dependence in the scattering process? And what we're going to show here today is that, and probably showed already part of this, is that for a free electron, a single point particle, the cross section is the so-called classical electron radius. It's just a measure of how big an electron is multiplied by this constant. And this is called Thomson scattering. When we look at a single electron, just one electron, but it's not free. It's part, for instance, it is the, it's a single electron on some nucleus. Maybe it's on, let's say, a nitrogen atom, which has had removed all but one electron. So we still have that one single electron. The radiation comes in and makes that one electron go up and down, oscillate in the electric field. The nucleus is essentially not moving because it's massive in comparison. And so it's not able to follow the high frequency. And that one electron has associated with it some binding energy. It's part of an atom. We said it was on a nitrogen ion, just as an example, with a single electron. So the charge on the nucleus is that of nitrogen, 6, I guess. And but the electron is oscillating, and it oscillates, and it has some natural frequencies at which it oscillates. For instance, between an n=1 and an n=2 level, that's a natural transition energy for an electron in that atom, in that ion. And as a result, it responds to the frequency of the incoming radiation differently. It depends on how close the X-ray frequency or energy, h bar omega, is to the resonant frequency. Okay, and you can imagine that for an electron on a charged ion, there are actually many of these resonances, and we might want to change this label to something a little bit more sophisticated than just an S, but there'd be a whole bunch of them. And in fact, if there was, so that's just for one electron. If there's a lot of electrons, then there's a lot of electrons that can be doing transitions, and they each have many transitions, and it's just too much to try to calculate. And we wind up measuring and representing this by a so-called oscillator strength. Okay, so now let me see what's next. Yeah, so this oscillator strength, we're going to be talking a lot about it, but this is an example for silicon of the real and imaginary parts of the oscillator strength. And it's there's a real and an imaginary part because there's absorption and there's loss. There can be energy loss. And just for instance, by absorption of a photon, it comes in and it actually does hit a resonance, and the bound electron goes up one level, one quantum step, the photon's gone. That's an energy loss. Because of that, there's an imaginary part to the oscillator strength. Okay, and there will be for the refractive index too. The wave is propagating into some material, some of it's being absorbed. That has to be represented by a loss mechanism. Okay. So, yeah, before I go here, does anyone have anything to say?
I have a quick question on the graph on the next slide.
Oh, yeah.
When we're looking at the real part of the scattering factor, what does it mean when it goes negative, like around 10 eV or 100 eV?
Oh, a really terrific question. So actually, let me go back a slide. Right here, how do I want to say that? You'll see it comes in the refractive index, but basically what it's telling you is that you've crossed a resonance, and the remember in the refractive index it was 1 minus delta. This would be where it became 1 plus delta, 1 plus something. There's going to be a change of sign in refractive index at this point. So we'll see that better in the next lecture, but it's a really wonderful thing. And in fact, for these EUV multi-layer coatings we've talked about, they actually have a change of refractive index from 1 minus to 1 plus just here. So for instance, we've talked about the refractive index of glass to green light. It's something like a refractive index of 1.5. But as you go towards resonances, you can actually change sign. Okay, I'll show you in a moment. It'll come. Ask me again, because we're going to see this again with equations, and you'll understand it better, I think, at that point.
Okay, thank you.
Yeah, good.
On the previous slide with the equations, the one before this, yeah. Is that F0 of omega, is that the real part, the imaginary part, both added together?
Oh, this, yeah, this is everything.
Okay.
So this is both. You'll see it in a moment. But and this sub or superscript, the superscript, I guess, is what I used, means there's a special condition where all of the electrons are scattering in phase with each other. We're going to spend a lot of time on it today. Okay? So I'll come back to that and answer you better at that time. But the magnitude of F, so F has a real and imaginary part, and this is the modulus squared of that. Okay, so I told you this, and this is where I just couldn't tell if anyone understood this or not, but I was using these Fourier transform methods, I should say Fourier Laplace methods. And if you have some complicated equation, if you have some equations and there are vector and time derivatives, if you introduce this technique, it allows you to what we call algebraize it. The time derivative becomes just an algebraic multiplier, and the gradient the del operator becomes an ik, where k is this is not the unit vector. This is k equals 2 pi over lambda, but it has a direction. Okay, and when we take this, so in doing this right now, so I'm going to go through this. What we want to know is if we make a model for what is our current density J, let's say for our point particle, what is the electric field going to be? We'd like to calculate for a little oscillating electron, so much smaller than the wavelength of the X-rays or light, that we can represent it as a point particle. What is the electric field it radiates? And then we're going to do okay, we know that the intensity depends on modulus E squared, and there could be some angular dependence. We're going to get all of that. And that's where we're going with this right now. We're trying to solve for the electric field for some current J. And we're doing it a little bit general because we need to do it for both the point electron, the free electron, the bound electron, and the atom. Okay, and so we're just going to go through the math, and then we'll write J for each of those cases. So this is just a repeat of the equation there. This is what it, if this wave equation in move to k omega, the phrase I would use is move to k omega space, looks like this, because this partial with respect to t became a minus I omega, so it's an omega squared. This is a del dot del, del squared, del dot del, so this becomes k squared, and there's a c squared in here. Okay, so this wave equation now looks like this in k omega space, and we can solve for E of k omega, divide through by this. Oh, it's got some interesting properties. You know, it has poles just where we have wave. We know there's waves. Omega equals k squared is the same as f lambda equals c, recall. So if we divide this through and we have some relationship for ek omega, then we can go back and transform back to find out what is the field in real space and time. So this carries over to the top equation here. We solve for ek omega, just divide through, and then we do the inverse transform. And now we have a solution for the electric field generated by some arbitrary current density in k omega space. And the T just means transverse. That came out of the transverse wave equation. This, you may recall, looks like a Green's function. And in fact, it is a Green's function. And it's allowing you to solve some mathematical equation in terms of an arbitrary source. So we're solving the wave equation for an electric field in terms of an arbitrary source. So that's called a Green's function. We have to do this integration, and depending on whether you've done these calculations recently or not, or had it in class, it may look complicated, but it turns out it's really simple. It is really simple if your mathematical skills are up to speed. And if they're not, please don't worry about it. The reason I'm showing you the slides in this manner is so that you can get a sense of how we do it, but mainly what we want is the answer. So there's a lot, this you could say, well, this is a lot of electromagnetics, which may be interesting to you. We certainly need it here, but you don't have, as far as I'm concerned, you don't have to be the master of all of these little details. So now I want to talk about an oscillating point charge. And I'm imagining that there's an electromagnetic wave coming by, and it has a direction, an electric field, and a magnetic field, and the electric field, oscillating electric field in the wave is going to make the electron oscillate. The B field doesn't have much of an effect, and I'll come to that later, okay? And so we're going to represent the current density as Q, N is the density, V is the velocity. Q is minus E, that's the charge of the electron. N is the electron density, which for a point charge is going to be represented by a delta function in three dimensions. So this delta of vector R is defined as meaning delta X, delta Y, delta Z, or some other coordinate system. And the delta function, you recall, is 0 whenever X is not 0, but when X is 0, it goes to infinity. And it's normalized, so this is a normalized delta function. So when we start doing that integration, we're going to get some help from these delta functions. So in the usual fashion of the Fourier Laplace transforms, jk omega, which I could remind you, I guess, we need jk omega. We only need the transverse component that's going to bring in an angular function, but we need jk omega. And here's how we get it, okay? It's the Fourier transform of the space-time J of RT, but the J of RT has this property, it has this functionality here, the minus E, a delta function, and a velocity component, B of t. So we have to integrate over R, vector R, 3 coordinates and time. The delta function really made that simple. And what we're left, we still have the minus E and we have the V, okay? And so what's left is this thing looks like the Laplace transform, if you will, of the velocity function. We took care of the R integral, we still have the V of t, and we still have the e to the I omega t and the dt. The dr integral is done. And this thing we recognize as V of omega. It's the Fourier transform of the velocity function. So jk omega is now solved. This is what it is. And if we only want the transverse component, meaning transverse to the propagation of the wave, this is what we've got. Okay, so I'll probably have to come back to this. But now we have the j to put in that Green's function. Okay. So shown here. Now I have to move this out of my way to see it. Okay. So so we have what is j, okay, going back, and we have this Green's function thing that we have to do. And we have to do this integration over all of omega, but omega hits a resonance, has a pole. Mathematically, it has a pole at omega equals plus or minus kc. Either way, either sign, it gets squared. So there's a pole at omega equals kc here, and there's a pole at minus omega kc. And if you're familiar with which integration technique, the Cauchy principal parts, you don't have to play this game, but it's not the one I usually teach in undergraduate math classes. But what they will teach is that actually omega isn't, this is a complex plane in K space, the real part of K, this is, and the imaginary part of K. And the wave propagation K, omega over C, so this is F lambda equals C, right? That actually the poles, the zeros here, are not exact, you could consider them to be not exactly on the real axis, because there'll always be some lossy process. It could be because there's actually absorption in atoms or something like that. It could also be just this a little tiny bit of scattering. The smallest part is mathematically all we want. We just want to have, if the wave is propagating along and a very small amount is scattered into some other direction, then then energy has been lost to the propagating wave, and therefore K will not be pure real, it'll be slightly off axis. Once that happens, you can decide whether to close in the upper half plane or the lower half plane, but at any rate, when you do the integration, you use the, you add the sum of the residues, right? So, yeah, the Cauchy integral theorem. And this integration now leads you to this result. So again, we don't have to go through all the steps here. You can see it in the slides. You can look at them later, or you can go through for much more in the book. But basically, our Green's function method has left us with a relationship for the electric field in terms of a current density. And that has now come down to this solution here. It has a 1 over r dependence. Well, that's good. The electric field should have a 1 over r dependence. And this was the Fourier transform of the velocity, but this minus I omega is actually a time derivative, okay? And so if you do this integration, there were some exponential things came together. This is what you get, that the electric field depends on the acceleration, but only on the transverse component. And at a retarded time, the electric field seen at a time t depends on the oscillation of the electron, its acceleration at some earlier time, depending on how far away it was, because the wave had to propagate towards you, towards your detector, let's say, okay? So electric field depends on transverse acceleration from some retarded time with a 1 over r dependence. So that is a classical electromagnetic solution, and we're going to use it for our X-rays. And by the way, we didn't say anything about this being X-rays so far. Okay, so here's the electric field, and here's our pointing vector. And if you remember, how do I want to do this? So we want to calculate the vector radiated power in all directions. So here's an here's our little point charge. It's going to be made to accelerate in some direction, okay? And we're going to ask, what is the radiation as a function of angle, capital theta, measured where the wave vector, the direction of the wave, is at some angle, capital theta, measured from the acceleration direction. And these are the other transverse unit vectors, okay? So the pointing vector we found is this quantity here, and we have the electric field here, and so we can put that in here, and we'll just put the modulus squared, okay? It depends, the pointing vector, the vector intensity basically, depends on the modulus of the electric field squared, so that's what's here, and it's going to go in a propagation direction k0, and it has a 1 over r squared. So power goes, electric field goes as 1 over r, power goes as 1 over r squared. And the transverse component of acceleration is the magnitude of the acceleration times the sine of this angle. So when this is 90 degrees, you have maximum power flow, okay? So an oscillating electron, we see at the bottom here, it's going to produce a donut pattern, which is maximum at 90 degrees. Okay, so this is the formula. This is what we've derived then as the radiated vector power is shown here. Okay, so it has this sine squared function and has the magnitude of A. Okay, and if we introduce an area as being some distance away and a solid angle times some distance away, and we write that the Poynting vector is the power per unit area in a K0 direction. This relationship can be written in this way. And this is what's called dipole radiation, little electron oscillating with an amplitude small compared to the wavelength. Okay, and so it's quite famous in both electrical engineering and physics. Okay, and this is the formula, and we're going to use it many times in the class. So don't throw this one away. We're going to use it here today because we're going to do scattering cross sections, but we're going to use it when we get to synchrotron radiation to help us understand why does an undulator at the ALS produce a watt of power, or at APS, why does it produce maybe 10 or 20 watts of hard X-ray power? We're going to use the same relationship. Okay, so that is called, excuse me, dipole radiation. So that was power per unit solid angle. We'd like to know the total power. Remember, we were talking about a scattering cross-section was the total scattered power in all directions divided by the incident intensity. So here's our integration to get power by integrating out the solid angle. And there's some geometry that you have to go through here, and not good for me to do it in class. You can follow it, I think, at home better in the book if you're interested. But basically, there's some integrations that need to be done here, and there's a solid angle the solid angle depends on the sine of the angles, sine theta, d theta, d phi, which you can recall. But so that's in the solid angle, but the power radiated per unit angle also had that dipole sine squared. So there's a sine cubed here, okay? And when you do these integrations, this is what you find for the total power radiated. This factor 8 pi over 3 appears, we're gonna see in a moment, and these factors here for the acceleration. So we'll have to calculate the acceleration of our point electron, okay? Free electron, bound electron, etc. But excuse me, this is the formula that we're going to use. And if the acceleration has a sine squared or cosine squared behavior, as it would for a propagating wave coming by, and we average this bar over the top means we've averaged over one cycle or over many cycles. But if we average over one cycle, we have an average of a sine squared omega t, d omega t, etc. cosine. That introduces a factor of a half. So this formula gets an extra half out in front. So this is now the total power scattered by a point charge with an acceleration a. So let's see now how we can use that. Here's our scattering diagram, and we've just figured out what is the total power scattered for an accelerated charge, and I've shown it as being power divided by the intensity, which is power per unit area, so it has units of area. Okay, so now this is just a classical case of an electron in the presence of a passing electromagnetic wave. So this is just F equals ma. This is the Lorentz force, minus E for the electron, the incident field, plus V cross B. And it says V cross B is small. And that's because if you did a ratio of E over V cross B using one of those relationships on an earlier slide, I think the second slide, you'll see that this term is of order V over C. So unless the electron is oscillating at near the speed of, some fraction of the speed of light, this term doesn't matter. And we're not going to be anywhere near that. So for our calculations here in this X-ray regime, and even for rather extreme nonlinear experiments that we might get involved in, basically all we have is the following. We just divide through by the mass, and we have the acceleration of this point charge is minus E over m times the electric field. And this could be e to the minus I omega, it could be E0, e to the minus I omega t, or we could write it as E0 cosine omega t, etc. Anyway, this is our acceleration. So we have a formula for the radiated power and other things, power per unit area, which depends on an A. Now we have what A is, the acceleration, okay? And so here's our, the average power scattered had that 1/2, it had the 8 pi over 3, and it had this formula here. This is what we had before, but there was a modulus A squared here. And now we've replaced modulus A squared by this term, E squared over M squared, and the modulus E squared. This is the incident field. So this is what we saw before for average power from an accelerated charge. Now it's in terms of the incident electric field. And the scattering cross-section is this power, this average power scattered to all directions. This was total power scattered. So this formula is here, 4 pi over 3 from this, all of these things here. And S, the magnitude of S is the incident intensity, which on an average, get to half in here, epsilon 0 over mu 0, and the magnitude of the incident electric field squared. And you can see, obviously see where these are going to cross out. The electric fields are going to cross out. There's epsilon zeros and mu zeros, and C, if you remember, is 1 over the square root of epsilon 0 mu 0. So a lot of those things, many of those things we're going to collect in the so-called classical electron radius. This is how it's defined. You can look it up in Jackson, for instance, if you use that book, but it won't say a whole lot more. It basically is an effective radius of the electron, where its effectiveness is that it equates the electrostatic energy stored in a uniform sphere of some radius, and it equates that to its rest energy. How accurate is that? Well, it's a convenient measure for us. And if you use that, you'll find that the scattering cross-section for a single free electron is this 8 pi over 3 times this classical, excuse me, electron radius squared. So a couple of interesting things. So this is named the Thomson cross-section after J.J. Thomson. It has a numerical value, which is seems quite reasonable for the size of an electron. And interestingly, it has no frequency dependence. So if you were to do laser scattering for plasma diagnostics, and
Did he freeze?
I think so.
Okay, I thought it was my computer.
I think everyone did.
Maybe it crashed. That's happened to me before. I'll probably be back in a minute. There he is.
You're muted, Professor.
You're muted, Professor.
You're muted. I don't know.
okay, so now you can hear me. And let's see if we get, okay, it'll take me a second to get back to this slide. You guys think of questions you want to ask? Oh, my goodness. Are we back in business? Hey, great.
Yes.
You have to go back a slide or two because something happened here. Okay, so this was the result we got. So we had this formalism that depended on the acceleration, but we didn't say what the particle was, except that we did the first, we had a formalism which just involved the acceleration of some particle. And then we went through and we said, okay, it's going to be a single free electron. We go through this combining terms and we got this simple cross-section with no frequency dependence. So now we're going to use the same formalism, and we're going to go to this equation of motion. So this is the equivalent. This is F equals ma. This is for a bound electron. So here's the Lorentz force. This we had written before as m dv dt, same thing as before. We've added two terms. We've added an oscillating natural frequency. So if you're far from the frequency, it won't matter. And we've added a loss term. So this is the equation that's used. Well, anyway, so this is the oscillation of a bound electron, meaning meaning it's bound to some atom or ion if there's been a few electrons removed, as in a plasma. But this is the equation of motion, and we're going to solve this for what is acceleration and stick it back in that same formula. So I had written this before as dv dt, but now I've written it as d squared x dt squared. I'm assuming that there's an X-ray wave, or actually any wavelength, visible light, that has an electric field incident with some amplitude and an e to the minus I omega t. And then I have the electron is going to oscillate at this frequency. It's the only frequency it's going to oscillate at because that's the driven frequency, okay? So if I solve this equation, so these ddt's become minus I omegas, and here's a minus I omega squared. And so all of these terms have an x in it, but they have different frequency terms. This is going to have an omega squared, an omega, and no omega. And if you combine, so then you can combine them and with only an x multiplying and divide through by all of that, get rid of the v cross b, and solve for x. So this x equals this. This is the solution to this equation. The minus e divided through by all the m's, and this is the omega squared. This is the resonant frequency, and then there's the lossy term. And if you take a second derivative of that, you're going to get a minus I omega squared. So minus omega squared. So this is the acceleration of a single bound electron oscillating in an incident electromagnetic field where that electron has a single resonant frequency. We'll extrapolate this later for more resonances and maybe more electrons. But anyway, we have the acceleration for this point particle, and we can put it back in those equations and go through the same things that we did before. And now the cross section is going to have this additional multiplicative factor. So yeah, go.
I have a question. So is x right here referring to the velocity of the
no,
particle?
X is the position.
So
X is a position, dx dt is a velocity, d squared
right.
x dt
It's an acceleration. Okay.
Yeah.
Okay.
Yeah, so it's the amplitude of oscillation in the electromagnetic field. Yeah.
Okay.
Okay, so this is our bound electron, and let's look at some examples. If omega, the X-ray oscillation, is close to the resonant frequency, for instance, a transition between n equals 1 and n equals 2, if the incoming radiation is close to that, there's going to be a very large cross-section. It's going to scatter like crazy. So for instance, for the plasma people in the class, this is a tool used for laser light scattering from certain ions that they'll put in the plasma, which have a very strong resonance right near that radiation frequency, okay? And they'll use it as a diagnostic because the cross-section will be, which is otherwise kind of small, the electron cross-section is kind of small. This could make it really large. Some other examples, if the frequency is very large compared to the binding frequency, or in terms of energies, if the photon, put H bars on all of these things, and this will be the photon energy, and this will be the resonant energy. If omega is a very high frequency, really way out in the X-ray region, this will become larger than this. So you'll have omega to the fourth, this will become omega to the fourth, and this will be large compared to the the lost part also, and you'll get back to the free electron, the single free electron case. So for very high X-ray energies, well above all the resonances, each of the electrons acts like a free electron. It's why when we were looking at that atomic scattering cross-section, why it leveled off, why F1, the real part, leveled off at roughly the number of electrons in the atom. So each atom at high enough X-ray energy, an atom will, the electrons will all act as if they were free, and the cross-section will just be the cross-section of all of those electrons actually acting in unison or coherence. Does someone want to say something before I switch, complicate matters a little bit?
Yeah, just a quick question.
Sorry, go ahead.
Yeah, we can have several.
Okay. What exactly is gamma? Does it have like a physical characteristic?
Yeah, in a second we're going to give a proper quantum mechanical, but it could be absorption. You know, this could be the child on a swing where you're pushing on the swing, and there's some natural frequency. You don't want to hit it, or you send the kid swinging around. But there's also some lossy mechanism where the ropes tie at the top to the hinges. So for an atom, it could be an absorptive mechanism. It could be absorption. Okay. But rather than spend time on gilding a lily with this simple classical model, let's wait in a moment. I'll show you that the classical quantum mechanics gives you the same result, and it has a much more meaningful interpretation. But there was a second question.
Yeah, I guess these are just models, but my question was like, since, I know the next one we're going to talk about is the multi-electron atom.
Mm-hmm.
So then would this really only apply to something like a hydrogen atom where there's only one electron, or are we sort of not worrying about that yet?
No, actually. So again, for the plasma people, they often wind up with a hot plasma where they, like, as one example I was quite familiar with of titanium, where they strip off, that plasma is so hot, it rips off all of the electrons and there's only one left. Okay, so it's called hydrogen-like titanium. It's only got single electron, but it's got 22 in the nucleus. So, okay.
Yeah, that makes a lot of sense.
Okay. Oh yeah, so here's a side example. So here's our formula for the cross section. Oh, good. This is a cross section, and one example that's really quite famous is called Rayleigh scattering. Why is the sky blue is one example, but in the case of Rayleigh scattering, you're not in the very high frequency. It's not like omega is much larger than omega s, but you're on the low side of the resonance. So if omega is smaller than the resonance. So for instance, this could be like let's say silicon again has an edge at 99 eV. Suppose you were scattering off it at 80 eV, some high harmonic experiment, okay? Omega, h bar omega would be less than h bar omega s. This would be 100 or 99 eV, and this could be 80 eV. So when omega is less than omega s, okay, and it gets squared, and it gets squared again. So it doesn't have to be a lot less. If it's only a half, you're gonna get this behavior. When this is less than this doesn't count anymore. It becomes small by the square and the square. And you wind up with omega s squared again. The minus sign gets squared. And you wind up with omega to the fourth over omega s also to the fourth. This could be present or not. And so that result, that is called Rayleigh scattering. It has the same free electron part out in front, but it winds up with an omega to the fourth over the resonant frequency omega to the fourth. Could be written inversely in terms of wavelengths. It's called Rayleigh scattering. He described this in 1899, and it is a strong wavelength to the fourth power. So in this case, the longer wavelengths don't scatter so much. The shorter wavelengths where in the denominator to the fourth power, they make a big difference. So that brings us to this baby. When you look up and you see blue light, you see a blue sky, it's because of this Rayleigh scattering, this fourth power, and it's because the oxygen and nitrogen molecules in the atmosphere have a resonance in the ultraviolet, around 150 nanometers in terms of wavelengths. But if you're looking up, first of all, if it were at night and there was no light coming in from the sun, you don't see anything but the stars. They're very weak, but they're out there. But in the atmosphere, there's all this O2 and N2. If light is coming in from the sun with all equal measures of all three wavelengths shown here, excuse me, red, green, blue, and they all come, the bound electrons in those oxygen and nitrogens are oscillating up and down, but they're oscillating much more, their acceleration is much stronger for the shorter wavelengths, and therefore they radiate more, and it's to the fourth power. So all those, so many of those bound electrons in those molecules are radiating. They're sending the light all over the place, but you happen to be down here and you get your share of it, and you just see more blue than you do of green and red. The green and red are there, but they're less by this factor. Okay? So that's all due to the bound electron being at, and the incoming radiation to be in the visible, which is a frequency well below the ultraviolet resonances. Okay. Just for completeness, this is when the sun is overhead and there's equal amounts of the radiation reaching the molecules above your head. You're looking up. But at sunset, where you've got the setting sun and the light is coming through, because of this scattering process, as it's coming through, as the radiation's coming through here, the blue is being scattered the most by the same fourth power. So by the time it gets to the molecules above your head, there's not much blue or green left. There's mainly red. You see a red sunset. If you look up, and there are some low clouds, those low clouds will also see red light, and you will see a beautiful red sunset. If you look around and there are some other clouds that are white, how is it that there are some clouds that look red and some clouds that look white? It's a matter of altitude. The ones that are in the lower portion of the atmosphere where they've lost all the blue and green, that cloud only sees red light, that's all it can scatter. So you see red light. If there's a cloud that's up in a higher level where there hasn't been much absorption, it's gonna scatter just like before, okay? It's up nice and high, okay. So now, now for the multi-electron atom. So here's an incident wave coming in with a k vector I. So this is not a unit vector. This is 2 pi over lambda. This is the incident radiation, and it has a vector direction. And so there's some wavelengths here, some plane waves here. And within this multi-electron atom, we'll say it has Z total electrons, and they're all whizzing around here on their own probabilistic trajectories, each represented by a delta function. They're all point electrons, but they're at different places, and we represent their positions from the center of the nucleus measured away by R, the coordinate R, and each of the this is the coordinate system, and each of the electrons, there is Z of them, so we're going to have to sum all these little delta particles. Each one of those electrons has some position shown here as delta RS, meaning this is measured away from the nucleus. And again, we're going to have to calculate the scattering cross-section, we'll have to look at the same classical equation as before, but now, and calculate the acceleration as before, but a new term is going to appear, which depends, it's a phase term. So all of the electrons are oscillating at the same frequency, omega t, e to the minus I omega t. So they're all doing that. But the radiation comes, let's say, comes to this electron here, and then it scatters in all directions. And you're interested in what was the path to get to your eye or your detector. Okay, and so you have to do some geometry here to track all the possible phase shifts. The path, for instance, the path to your eye is longer to go, let's say, to this electron and scatter to you than it is to go to this electron and scatter to you. And to calculate the difference in path length, you need to go through this geometry here. Okay, and I'm not suggesting that we try to do that now, for sure. But what you'll find is that the acceleration for each of those subscript S electrons is going to have a new phase term in here, which is different from every electron. And it's K incident times delta RS, which is the difference measured from the origin of the nucleus, the center of the nucleus. There's a path difference for each electron, which geometrically you can show is this DRS, delta RS. So I did this carefully in the text, and there's not a lot of other places I found it, although Jackson does have it. Okay. Anyway, if you go through, you'll find out that the acceleration by a certain electron S has slightly different, looks like amplitude-wise looks the same as before for a single bound electron, same frequency dependence, but the phase is a little bit different. So when it's reaching your eye, it may have a different, each of the electrons is contributing a slightly different phase. So it's a geometry challenge to go through all of this. But if you do, and you take this acceleration, and as before, you solve for the electric field, you'll get the same things that you saw before, but there's going to be these extra terms in the exponent, which have to do with phasing and distances between the different electrons. So if it turns out, so that we're going to see that there's some measure where this term matters, and sometimes it doesn't matter. If it matters, you're going to get a highly angular dependent scattering, and there's going to be nothing you can do about it, or not much you can do about it. But there are some cases where it goes to zero quite conveniently, and that's what we're going to look at those two now. So I've written this slightly different this time. I wrote the electric field in a manner that I might have written it before, but now it has the summation because there's Z different electrons, and it has this phase factor, okay? And this thing in brackets we call the atomic scattering factor. This whole thing, including the sum and all of the phase effects and all of the frequency effects, are all captured in this atomic scattering factor. And where this is non-zero, it means that you're going to wind up getting really interesting angular effects. But there, even, for instance, when we do scattering, SACs or other experiments, you're going to see that I think largely this is going to go to zero for us. And by the way, just notice that the atomic scattering factor is a multiplier. It's multiplying the electric field of a single electron by some factor which is representing all of the electrons in the atom. And it is a complicated thing, again, summing over all the resonance of all the different electrons. Okay, so what about this, this factor here? This delta K is this delta K. This is a scattering diagram I told you about before, and I think I'm going to have time to mention it again. But if you have radiation coming into some volume of material with a K incident, and there's some fluctuation going on there, it could be like the periodicity in a grating or a multi-layer, or it could be a sound wave represented by this delta K. This is representing the medium, the density variations, okay? And they will add up to the new scattered direction. So incident direction something going on in the material, and it comes out this is a lowercase theta. Okay, so this delta K is this thing, and it has a magnitude. This is basically Bragg's law here. It has this magnitude, and this delta K depends on this angle. And so if the angle is relatively large, this could be large. But as this angle becomes very small, it's kind of like forward scattering, then delta K becomes small. So let's look at what happens to this atomic scattering factor. Here it is just rewritten, and we're interested in this factor here. When might this be something we can deal with? Okay, so we'd like to know what's a measure of this, delta K, delta RS? Well, delta RS is sort of the radius of the various electrons. So let's represent it by a Bohr radius. So delta RS, we're going to say magnitude-wise, it's A0, it's the Bohr radius. All of the electrons are more or less contained within that distance. And delta K, from the diagram we saw before, has this sine theta over 4 pi sine theta over lambda. So that's from this thing, okay? So you could say, okay, this complicating factor here goes to 0. This goes to 0 in two cases. One if lambda is large, and one if theta is small. Either one of those will make this thing go to 0 or become small. So here they are. Here is where the long wavelength limit, we call the one where lambda is much larger than the Bohr radius. So this says that the wavelength of light is large enough that all of the electrons are seeing the same incident field as each other, okay? And it just simplified everything so much. And the other thing is if the angle is really small. So if the scattering angle is so small that the incident vector and the scattered vector are almost co-propagating, actually they might be co-propagating, then delta K will be very small, okay? And that's this case. And forward scattering is it. And when that happens, when either of these is the case, I chose to represent, so that means this goes to 0. This is what's left over. We put a superscript 0 on it. The reason we put it as a superscript and not a subscript is because, remember, this is a complex quantity. So we're going to wind up, the tradition in the community is to use it as F1 plus or minus I F2, subscripts on F for the real and imaginary part. So the superscript 0 means that this phase term is negligible. Did I get what I wanted? So what is that saying? That's saying, for instance, if the wavelength here is so long compared to the atom, the wavelength is much, much larger than the atom, then all of these electrons are basically seeing the same phase, and the phase difference in propagation is also not much because the difference here is not much. So basically, that's what the long wavelength limit is. The other limit is when they're looking not at some angle like this, but when the incident radiation is coming straight on, the phase that this electron sees, the front one, is different than the phase of the one closest to the observer. There's a phase difference here for the oscillating electric field, for what those electrons see. But the phase difference going this way in the forward direction is canceled out by the phase difference going ahead. So there's an incident phase difference, and then there's a scattered phase difference. And one cancels the other in the forward direction. And by the way, that is going to make refractive index calculations much simpler. Okay, so this is our atomic scattering factor in this interesting limit. I'll call it the long wavelength limit, but it also means forward scattering. Okay, and so this is what we were showing before in the calculations. And again, this is written for a lot of electrons on an atom with many, in this case, classical resonances, which we're going to deal with in a second. So just to make it clear, here's our simple model of the atom. It's got a lot of electrons and some radiation is coming in, maybe with a wavelength that's long compared to this, or maybe it's not. If the wavelength is long, the phase problems don't matter. But if the wavelength is short, where you're using an X-ray wavelength of a ½ angstrom, it matters a lot, okay? And also for each of these atoms, there's not just a little omega S, a little characteristic oscillation frequency. There are many possible transitions from one level to another for each of those electrons. So this is it could be a monster, okay? So anyway, all of that gets wrapped into what we will call the atomic scattering factor, written as this. Here's the real and imaginary part. And I'm going to show you just in a moment. How many moments do we have? We have a few moments, so we're good. So where this represents absorption, and this represents just pure scattering. And I just tell you, in case some of you people who work with hard X-rays, in the hard X-ray region, omega may be so large compared to most of the resonances that this won't matter so much. And this thing will, this Z, F1, the real part, will get pretty close to Z for that atom. So for silicon, this thing in the graphs that we saw before kind of was leveling off near Z equals 14, okay? So for people who deal with really hard X-rays for diffraction from crystals at say 20, 30 kilovolt, they will write this thing on the right as Z minus F1. They still have the minus F2, but they'll have Z minus F1 because they're so close to Z to start with. This is just a summary slide, okay? Except that basically for all of these oscillations here, there's we're going to sum, for instance, for a single electron, we have to sum over all of the, if there were different resonances, we would have to sum over what we would call oscillator strengths. So you can see we're copying here. We're looking forward to the quantum mechanical model. The atomic scattering factor will have all these frequency components, but it could have a summation over different resonances. And those resonances would have to be normalized. For instance, for a single electron, these would normalize to 1. If you added up all of the oscillator strengths, they have to add up to 1. If you have a lot of electrons, Z electrons, this is the oscillator. This is the summation of the oscillator strengths would be Z, the total number of electrons. But let's leave that as it is. In the end, we wind up measuring these things in the laboratory for all the frequencies we know, and we get the real and imaginary parts. We actually measure the imaginary part, and from that, we get the real part. We use what's called Kramers-Kronig relations, which you'll have to ask me. Okay, so here's an example of carbon. This is F1 and F2, so here's the absorptive part, which is, it's absorbing photons. So as the wave propagates through some thin film of carbon, it's being absorbed. And how much it's absorbed depends a bit on how close it is to one of the resonances. Here's a photon energy less than the carbon K edge, and the absorption is going down, down, down. But all of a sudden, the photon has enough energy to kick an electron from the K shell out. And there's absorption. So the absorption just jumped up, and then it starts going down again, okay? The real part, shown here, you see as you increase photon energy, that part of the oscillator strength basically levels off at 6, okay? So this is an interesting example because this is saying that there's, for a carbon atom, right, let's say right around here, somewhere around here, for this wavelength, let's say for 2000, for a photon energy of 2000, the wavelength is still long compared to the size of the atom. So all 6 of those electrons are oscillating together in phase, in phase in every direction. And as a result, the cross section, well, as a result, F1 goes to Z approximately, but the cross section depended on F1 modulus squared. So it winds up that you can get a cross section, the circumstances are right, that goes up as the charge on the nucleus squared, the number of electrons squared. So for carbon, in this region, in this photon energy region, you can get a Z squared effect. If you go out to very, very harder X-rays, absorption will be dropping off, but the wavelength won't be so long compared with the atom, and you won't get the Z squared effect. So we call this an N squared effect. N is the number of electrons. And those things come up very frequently in our class.
Professor?
Yes.
I'm a little confused, like what it means physically when F1 goes above 6. Like it goes above Z for a second.
Okay, well, as a statement of honesty, so am I.
Okay.
Let me think about that one, but I noticed it too, yeah.
Okay.
Okay. But we had just a few, so I don't know why I'm showing this again. This is F1 and F2. F2, the imaginary part is related to mu. So there's a direct relationship between F2 and mu, the absorption coefficient, the one that was called mass absorption coefficient, even though it absorbs photons, not mass. Shown here quickly, this is for silicon. And we were pointing out before that this is interesting that it crosses, it goes negative. What does that mean also? But let me think about that and come back to you on that. And the absorption in silicon, this is right near the absorption edge, which is 99 eV. So for photon energies below that absorption edge, it's absorbing like it's less, although it's got 14 electrons, it's absorbing like there's only 1 electron absorbing. Okay, and it's scattering like nothing. But when you get up, anyway, so that's good. For silicon, it's almost like it's not there. But for molybdenum, remember the silicon molybdenum multilayer, it turns out, just happenstance, that its absorption is like 1 electron, equivalent to 1 electron at 99 eV, but its scattering is more like 15 or 14 or something like that. And you say, well, how could that be? Well, the photon energy is low enough that most of the electrons are too tightly bound and they're not absorbing it. But there are outer electrons which aren't absorbing, but they can scatter. And so the combination is what made this moly-silicon multilayer capable of happening and getting such a high reflectivity. And this is the one that was used for the EUV lithography. I'm missing one slide, but the next lecture will be on refractive index, and I'll bring it in then. This is just pointing out to you the utility of a general scattering diagram, where, just to describe it here, there's an interesting little thing which you can use to your advantage many times. Here's incident radiation, some medium. It could be a crystal. And this is the periodicity of the crystal. It could be a multi-layer coating. It could be an acoustical wave in sound. I'm talking, there are sound waves. You can do scattering off sound waves. Or it could be a plasma wave, an electron plasma wave, and you're scattering off it, and you can use that. So laser scattering, basically Thomson scattering, laser Thomson scattering off a plasma, picks out where the waves are and scatters them in a new direction with a new frequency perhaps. And so this, we can understand this scattering process if we look at the current density that's going to go into Maxwell's equations. Okay, we write it this way. So there's a density term and there's a velocity term. If we did the Fourier transform, we'd have our amplitudes, J and N and all these amplitude factors, but the the velocity would have this amplitude. It feels an electric field. It has a certain mass. There's a frequency. Each term has some frequency and wave number exponential. And so this is the one for velocity. This is a representation of the electron density. It's e to the minus I, and there's some frequency and wave number associated with that wave. So if it's moving, it has its own frequency, and it has some periodicity here. Okay, that's represented here. So the velocity picks up all of those things from the incident wave. But the density, this is the crystal. For instance, if the crystal is not moving, omega d is 0, but this would be 2 pi over d, the interplanar distance, okay? This is just the amplitude. And anyway, if you match, this is the scattered radiation, which depends on the incident wave and the density or modulation in the material. And if you just match the exponents, you know the amplitudes are going to match. We sort of did that. But if you just look and match the frequency parts, because they all, whatever the frequency is here, it must be equal to the exponent, the frequencies here summed. So just matching the exponents, you'll get that the scattered radiation has a frequency equal to the incident radiation frequency plus the frequency of the oscillation here. So again, for a crystal, this would be 0. But for a plasma wave, not 0 at all. Could be quite comparable. Also, the K vectors add. That's the K incident and the K scattered. Looks like this, okay? K incident, some representation of the density modulation in the material leads these. This is an isosceles triangle when this frequency is 0. But this is the vector diagram. It doesn't have to be isosceles, but if the motion here, the frequencies here in the medium are small compared to the incident frequencies, it'll be isosceles or closely so. This is a general scattering diagram, which you will find so many uses for. And I'll just show you that if in the case of a crystal, the crystal planes are not moving. They may have a little vibration, but let's leave that aside for the moment. Then omega S equals omega I. Omega S and omega I are equal. That means the wave vectors have the same magnitude. If they both have the same frequency and they're propagating in vacuum, they must have the same magnitude. So this is an isosceles triangle. And this KD, this is 2 pi over whatever the periodicity was. If you take this vector relationship, just, well, if you look at the diagram, just solve for the sine of the angle. It's this KD, the magnitude of KD, again, a 2 pi over something. It's half of that. It's half of this divided by the hypotenuse. So the sine of the angle is this. There's a lot of 2 pi's here. You can get rid of them. And this will be 2 pi over lambda. The lambda goes to the top. And this is 2 pi over d. The d goes to the bottom. The sine of theta equals lambda over 2d. Or if you solve, lambda equals 2d sine theta. This is Bragg's law. So we've used these very general scattering relationships in a practical case. And by the way, you could put h bars on all of these things, and then these would be photon energies adding and momenta. So this is conservation of energy in that case and conservation of momentum for a scattering process. So again, it's useful. So we're going to break now, and next time we come back, we'll be in chapter 3, and our main goal will be to get the refractive index, and I'll try to answer some of those odd things that we observed.